Hello students, welcome to the next video lesson on electric field. This video lecture deals with the topic of electric flux. Electric flux is a physical quantity that has a direct link with the electric field lines. It is used to represent the number of electric field lines cutting normally through a given surface. Let us look at this figure. It represents a rectangular surface ABCD having area delta S receiving electric field lines perpendicular on its surface. We can see that the number of electric field lines falling on this surface depend on two factors. One is the intensity of electric field. We know that greater the intensity of electric field, greater will be the density of electric field lines in the given region. Thus, the number of electric field lines or electric flux associated with the surface depends on the electric field intensity in the given region. Another determining factor is the area delta S of the surface. We can see that greater the area delta S, greater will be the number of electric field lines passing through the surface. There is yet another factor that determines the number of electric field lines passing through the surface. This factor is the orientation of the surface. Let us look at the next figure. In this figure, we can see that the same rectangular surface ABCD has been kept in an inclined position. We can see in this case that the number of electric field lines falling on the surface does not depend on the area of the surface ABCD, but rather depends on the area of the surface AB-C-D, which is the projection of the given surface ABCD in a plane receiving the electric field lines normally. In this last figure, we can see that the surface ABCD has been kept in such a way that the electric field lines are tangential on the surface. In this case, we can see that no electric field line is cutting through the surface. Thus, in this case, the electric flux associated with the surface is zero. Thus, we see that the number of electric field lines or electric lines of force, in short ELF, depends on number one, electric field strength in the region, number two, size of the surface, and number three, orientation of the surface. Here in this figure, we can see that theta is the angle between the surface ABCD and its projection AB-C-D in the plane receiving the electric field lines normally. Through a little mathematical discussion, we can see that the area of the surface AB-C-D will be delta S cos theta as represented here in the figure. In these figures, we can see that electric flux depends on field strength mod E and area delta S cos theta, which receives electric field lines normally. Thus, we define mathematically the electric flux delta phi through the surface delta S as the product mod E multiplied by delta S cos theta. Thus, delta phi is equal to mod E into delta S cos theta. Here, we will represent the area of the surface as a vector quantity with direction along the outward normal. Here we can see that the unit vector n cap represents the direction of the area of the surface ABCD. We can also see that the angle theta is also the angle between the electric field and the normal to the surface, representing the direction of area vector associated with the surface ABCD. So, electric flux associated with the surface is given by the dot product of E and delta S vector, where delta S vector is the area vector associated with the surface ABCD. As we can see, it is a scalar quantity. The reason is that it is the dot product of two vectors. You can easily see that the SI unit is Newton per Coulomb meter square. All this discussion is applicable if the surface is a surface of uniform electric field. In case the electric field in the given region is non-uniform, we use the advanced definition involving the integral delta phi is equal to integral E vector dot delta S vector. The idea is that the whole surface is divided into small elements, and we find out individual electric flux associated with each small element and then add up the electric fluxes associated with all the elements into which the surface has been divided. Because the electric field is non-uniform, so the number of elements of the surface will be infinite, and so in that case, in order to add up electric fluxes associated with each surface, we will have to integrate. Thus, the electric flux associated with the surface, delta S, kept in a region of non-uniform electric field, is given by delta phi is equal to integral E vector dot ds vector over the surface delta S. The surface under consideration may be a closed one, and in that case, the flux associated with the surface is given by the integral E vector dot delta S vector. In order to indicate that the surface is a closed one, we put a small ring over the surface as shown here in the figure. The integral involved here is called surface integral of electric field. Both the integrals are surface integrals of electric field. The only difference is that in the second case, the surface integral has been taken over a closed surface. So students, with that we come to the end of the topic electric flux. Our next topic will be on discussion of another very important theorem called as Gauss's theorem, which is again one of the fundamental theorems of electrostatics.